Okay, the joint probability density function of two Gaussian random variable is given as fxy of x comma y is equal to 1 by 2 pi sigma x sigma y root of 1 minus rho square. It is rho square exp of minus 1 by 2 into 1 minus rho square x minus x bar square by sigma x square minus 2 rho x minus x bar y minus y bar by sigma x sigma y plus y minus y bar square by sigma y square. This is the formula. Now we'll discuss the properties of Gaussian random variable. Properties of Gaussian random variable. The first property says that the Gaussian random variable can be obtained from first and second order movements. Okay. What is the first order movement? First order movement is nothing but the mean value. The second order movement is nothing but the expected value. Yes or no? So the Gaussian random variable can be obtained from the first and second order movements, that is by mean. What are the things you require to obtain Gaussian random variable? We require mean, variance and covariance. Okay. And correlation coefficient rho. Covariance, if you know covariance, you can find out correlation coefficient. Okay. So to obtain joint probability density function of a Gaussian random variable, we require first order and second order movements. First and second order movements. Okay, that is, we require, if you observe this equation, what are the things we require? X bar, and we require variance, covariance and rho. Okay, so if you know this, you can obtain the joint probability density function of Gaussian random variable. The second property says that we have observed this. If two random variables are uncorrelated, if these two are uncorrelated, and we also say that we have seen that the uncorrelated random variables are also independent. Okay, that is, uncorrelated random variables are also independent. This is our second property. Here we have only the statements. Okay, so this is our second property. The third property is that the random variables which we are getting by linear transformation are also Gaussian. That is, the random variables whichever we are getting from linear transformation. So we are using transformations to convert one random variable to another random variable. Okay. So whichever random variables we are getting from linear transformations are also Gaussian. This is our third property. Okay. The fourth property is that the any k-dimensional marginal density function that is obtained from n-dimensional density function are also Gaussian. So here, for example, if you have n random variables, okay, from this n random variables, if you are finding only k marginal density random variables, okay, marginal density random variables, this marginal density random variables, okay, k dimensional, this is n dimensional, you have n number of random variables. Here how many random variables we will be having? K number of random variables, k dimensional marginal density functions, okay, that can be obtained from, that we are getting from, okay, getting from, so from where we will be getting? From n dimensional, because from n dimensional only we are obtaining this n dimensional density function. Okay, so these are also Gaussian, because the n dimensional Gaussian random variables whatever we are taking is Gaussian random variables. Okay, from this n dimensional Gaussian random variables, if you are taking only k dimensional random variables, okay, so you are getting k dimensional marginal density functions. Getting from n dimensional marginal density functions are also Gaussian. That is our fourth property. Okay. And fifth property says that the conditional density functions. Conditional density functions we have discussed, no? The conditional density functions obtained are also Gaussian. Okay. So we are obtaining these conditional density functions from the n-dimensional random variables, are also Gaussian. Okay. So these are the 5 properties of Gaussian random variable. What is the first property? First property says that Gaussian random variables can be obtained from first and second order moments. That is, we have to have mean, variance, and correlation coefficient rho. To obtain rho, what you require? Covariance also, some. And the second property says that if you have uncorrelated random variables, the uncorrelated random variables are also independent. The third property says that the random variables obtained from linear transformation are also Gaussian. Okay. And fourth property says that the k-dimensional marginal density functions getting from n-dimensional density function are also Gaussian. And sixth property says that the conditional density functions. How do you obtain conditional density function? So we will be obtaining like this. It is fx1, okay, x2, so on. So we are taking only k dimensional. So we get x1 to xk. Okay. And the random variables are x2 to xk with the condition that k x1 plus 1 is equal to x plus 1, so on. K xn is equal to xn. Okay. So with this condition, whatever the conditional density function we have obtained are also Gaussian. Okay. How do you define conditional density function? F x1, x2, so on, xk, x1, x2, xn, xk, where next variable xk plus 1 will be equal to xk plus 1, so on, xn is equal to xn. So this is the conditional density function. Whichever conditional density function you are obtaining is also Gaussian. Okay, these are the properties of jointly Gaussian random variables. 5 properties.